Hello everyone, welcome to the video on From Convolution Operation to Neural Network by Society of Artificial Intelligence or SOAI. I am Ritul and this PPT is created by my colleague Tushar. Let's start. From Convolution Operation to Neural Network. How is the convolution operation related to neural networks? Part 1. The following diagram illustrates the similarities between the convolutional operation and DNNs. As we can see from the diagram, both the highlighted output neuron and the highlighted convolutional output are essentially weighted sums of the inputs provided to them. Let's look at a direct comparison. This is the comparison between neural network and convolution operation on image on the basis of input, output and neighborhood. Let's start the comparison. On the basis of input, numerically input values for neural network and for convolution operation on image, the RGB values for each pixel in the image. For output, neuron which takes weighted sum of inputs as its input, it's for neural network. And for convolution operation on image, pixel which takes the RGB values transformed with a filter. And lastly, neighborhood. For neural network, all inputs from the previous layer contribute to the output calculation. But for convolution operation on image, only a localized neighborhood of inputs is considered for each output pixel. The entire convoluted output image corresponds to a whole layer of neurons. With multiple filters, multiple convoluted outputs each correspond to separate layers of neurons. Now, part 2. Let's look at the image classification task as it would have been performed with machine learning. Here, we flatten a 30 x 30 x 30 image into a 2700 row pixels and feed them as input to a classifier such as support vector machine or naive Bayes. There isn't much intelligence applied on the input side. Now let's look at the image classification done with some input processing. Here we realize that there are certain aspects of the image, which are outlines or edges, that are much more critical to the classification task than other aspects. So, we perform feature engineering whereby we apply some transformation to the input pixels before passing them into the classifier. Let's look at the use of feature engineering with the zero hidden layer NN to classify the images. Here, using a deterministic algorithm like HOG or SIFT, we get a better representation of the input by cancelling out useless information. We now use these new inputs as features for our neural network and learn the weights for the classifier. However, in step A, the transformation performed on the input image was static, without any learning, making it a handcrafted set of features. The only learning that happens is in the classifier. However, in a deep neural network, the input features are not directly fed to the classification. Instead, they are passed through hidden representation layers where they are distilled down to more input features before being passed into the classification layer. This is why deep learning is also called deep representation learning. In the above case, we allow the DNN to learn the representation weights and apply it to the features in steps before finally passing it onto the output layer. As you can see in the screen, the image is monument, not car, bus or flower. Now part 3. So far, we have intuitively determined what kind of transformation to apply to the input image before passing it through the classifier. For example, we saw that performing a detection yielded higher accuracy. Now, another thing to think about is why must we leave the choice of transformation to our human intuition? Why can't we let the DNN learn for itself the best transformation to apply? Why not let the network learn the multiple feature representation? Another point to consider is that we might not necessarily benefit from only one transformation. So letting the DNN learn the number of transformations to perform is also very useful. Here, we are not concerned with the type of transformation that occurs, so long as the overall loss or error is reduced. In the above image, we cannot say that the transformations are anything definitive like edge detection or blurring, but still choose to accept them because they lower the loss. Why not let the network learn the multiple layers of feature representation? It stands to reason that we can consider several transformational layers like the one seen in the previous example. The above process is quite similar to what we have learned in the DNN. There are three sets of weights, layers, and one for the classification layer. These weights are calculated using backpropagation. The only difference between a DNN and weights we are looking at now, CNN, is that for a CNN we only consider a small localized neighborhood of inputs when calculating the output instead of the entire input layer as in the case of DNNs. In a nutshell, for CNNs, instead of learning the final classifier weights directly, we should also learn to transform the input into a suitable representation through multiple layers of representations and learn the kernel weights for all of the representations instead of using handcrafted kernels. Understanding the input-output dimension. As we have seen before, a CNN can be compared to a normal neural network. The difference being that CNNs take the RGB pixel values as inputs and output calculation is done with a localized neighborhood of inputs. Consider the following diagram of a CNN. Let us dissect the first convolutional operation in form of above diagram. We are analyzing the convolutional operation on the gray input layer. The input dimensions are as follows. Wi is 227 and Hi is also 227 and Di is 3. The filter is of scale f, which is 11, that is 11 cross 11 cross 3, where 3 is the same depth as Di. We apply 96 filter operations, so therefore K becomes 96. We do not take any padding, that's why here padding is 0 and we choose a stride length of S, which is 4. Thus, going by the above information, the output volume can be calculated as follows. Here, the output is 55 cross 55 cross 96, as W0 is equal to Wi minus F plus 2P by S plus 1. Similarly, for H0, H0 is equal to H1 minus F plus 2P by S plus 1. It's also equal to 55, and D0 is equal to K, that is 96. Sparse connectivity and weight sharing. We already have an intuition of how CNNs are different from DNNs. The key point being that in CNNs we take a weighted aggregation of a neighborhood of inputs instead of all the inputs like in DNNs. Also, it is better to visualize CNNs in terms of matrices than by flat vectors as in the case of FFNs. More formally, two of the main aspects of CNNs are sparse connectivity and weight sharing. Let us look at the connectivity difference between DNNs and CNNs. The above diagram is meant to illustrate the difference between DNNs and CNNs with regards to the input-output relationship. In CNNs, as the kernel moves over the input image in strides specified by the stride length S, it passes over the highlighted regions as shown in the figure. The highlighted regions vary in size with a kernel size f, and they correspond with the input regions that are used to calculate the output for that particular neuron. For the CNN, neuron H11 corresponds to inputs 1, 2, 5 and 6, while neurons H12 corresponds to input 3, 4, 7 and 8. In contrast, in the DNN, neuron H11 and every other neuron corresponds to all input 1 to 16. This is why DNNs are called fully connected and CNNs are said to be sparsely connected. Now, let us look at the concept of weight sharing as illustrated in the figure. Here, we can see how weights are shared across an entire layer. In CNNs, weights are nothing but the kernel, and the kernel remains constant as we pass over the entire image, creating different neighborhood of inputs. One complete pass of the kernel over the image constitutes one convolutional output. As we have seen earlier, it is possible to have multiple convolutional kernels over the input. For each of these convoluted outputs, the kernel is constant, thereby the weights get shared for all the neurons in that output area. Only the inputs vary. By combining all of these convolutional outputs, we get one convolutional layer. Instead of treating the convolutional layer as a flat vector, we treat it as a volume, whose depth is given by the number of kernels used to process the input. By this practice, we are effectively reducing the number of parameters yet still retaining model complexity, thereby overcoming one of the shortcomings of DNNs. Max pooling and non-linearity. Let us look at a diagram of a CNN to better understand what max pooling does here. As we have discussed earlier, the first operation performed is a convolutional transformation using a filter. Here, by passing the filter over an image, that is with or without padding, we get a transformed matrix of values. Now, we perform max pooling over the convoluted input to select the max value from each position of the kernel, as specified by stride length. Here, we select a stride length of 2 and a 2 cross 2 filter, meaning the 4 cross 4 convoluted output is split into 4 quadrants. The max value of each of these quadrants is taken and a 2 cross 2 matrix is generated. You can see in this diagram. From a 4 cross 4 matrix with max pool, 2 cross 2 filters with stride 2, a 2 cross 2 matrix is generated with values 8, 4, 7 and 5. Max pooling is done to select the most prominent or salient point within a neighborhood. It is also known as subsampling as we are sampling into a single value from a region. Similar to max pooling, average pooling is also done sometimes and it's carried out by taking the average value in a sampled neighborhood. The idea behind max pooling is to condense the convolutional input into a smaller size, thereby making it easier to manage. Our first convolutional neural network, CNN. The following diagram illustrates the configuration and working of a convolutional neural network. It follows the LatNet architecture created by Jan LeCun. Let us sequentially break down the various layers in the CNN input. The image takes 32 cross 32 pixel inputs. There is no depth component because the images are in black and white. Convolution layer 1. Here, the filter size f is 5 and the central cell is the pixel of interest. Stride length as is 1. We use a tool of 6 filters, that is k is equal to 6. No padding is used, that is p is equal to 0. Each of the filters generate 28 cross 28 output calculated using W0 and H0 formula. Our hidden representation at this layer is A1, which is 28 cross 28 cross 6, where D0 is equal to K. Non-linearity with 10H and ReLU preferred for CNN is applied to A1 making it H1. If we were to proceed as a fully connected network, we would have an extremely large number of parameters. However, in this sparsely connected network, each of the 6 filters is of size 5 cross 5 cross 1, so the number of parameters would be much more manageable, that is 150 parameters. This is significantly smaller than in a fully connected network, therefore reducing the chance of overfitting. Here, the values f, s, k, and p, etc. are all counted as hyperparameters. Max pooling layer 1. The hyperparameters are as follows. Filter size is 2, stride length is 2, number of filters 6, and padding is 0. Here from a 2 cross 2 filter, we select only one value. Therefore, a stride of 2, the output dimensions are half of the input dimensions, that is 14 cross 14. We apply the max pooling independently to all 6 of the H1 layers, giving us H2, that is 14 cross 14 cross 6. No parameters for this layer as we are simply choosing the largest value in the filter and not applying any weights to it. Convolutional layer 2. The hyperparameters are as follows. Filter size f is 5, stride length is 1, number of filters k is 16 and padding is 0. Thus, the filter dimensions are 5 into 5 into 6. Here, 16 filters are applied to the input H2, thereby giving us an input depth of D node which is 16. Calculating W node and H node using the formula, we get 10 by 10. We get 10 cross 10. Our hidden representation at this layer is A3. Non-linearity with 10H and ReLU preferred for CNN is applied to a A3 making it H3. The number of parameters for the filters is 2400 parameters. This is much smaller than what we would have had in a fully connected network. Max pooling layer 2. The hyperparameters are as follows. filter size 2, stride length with 1, number of filters k is 16 and padding is 0. Here, from a 2 cross 2 filter, we select only one value. Therefore, for a stride of 2, the output dimensions are half of the input S3 dimensions. We apply the max pooling independently to all 16 of the H1 layers, giving us H4, which is 5 cross 5 cross 16. No params for this layer as we are simply choosing the largest value in the filter. Fully connected layer 1. Number of neurons are 120. Input is H4 flattened, that is 5 cross 5 cross 16, that is 400. Number of parameters in H5 is, you can see, 120 multiplied with 400 plus 120 minus bias, which comes out 48,120 parameters. Fully connected layer 2. Number of neurons 84. Input in number of neurons in H5 is 120. Fully connected layer 2. Number of neurons 84. Input is number of neurons in H5 is 120 and number of parameters in H6, which is 10,164 parameters. Now output layer, number of neurons are 10, input is number of neurons in H6 which is 84, number of parameters in Y is equal to 850 parameters. Overall, this combination of convolutional and fully connected layers is much more efficient than an entirely fully connected network. It has a significantly lower number of parameters but still is able to estimate functions of very high complexity. Training CNN. Let us consider a regular feed-forward network. Here, we obtain y cap as a prediction and use it to calculate the loss. Using the loss value, we backpropagate to calculate the gradients with respect to each of the parameters. Using the gradient descent update rule, we update the weights such that they minimize the loss. Now, we can carry over all of these processes to a CNN with a few small modifications. A CNN can be implemented as a feed-forward network wherein only a few weights are active and colored. The rest of the weights gray remain 0. Thus, we can train a CNN using backpropagation by thinking of it as a FFN with sparse connections. However, in practice, we don't do this, as most of the weights in the matrix end up being 0. Frameworks like PyTorch and TensorFlow don't end up creating such large matrices and only focus on dealing with the weights that are to be updated. Now, summary and what next. By the universal approximation theorem, we have learned that DNNs are powerful functions, approximators. They can be trained using backpropagation. However, due to the large number of parameters, the function can become extremely complex, resulting in a high chance of overfitting the training data. We looked into CNNs to see if we could have a neural network which are complex, but with fewer parameters and hence be loss prone to overfitting. CNNs solve both of those shortcomings with key points such as weight sharing and sparse connectivity. Non-linearity functions such convolutional layer. Training CNNs is also very similar to training FFNs, the only difference being we take a zero value for all weights that we are not interested in. We will then be able to apply learning to the filters, parameters, thereby reducing the overall loss of the CNN. They can be easily implemented with frameworks such as PyTorch or TensorFlow. Society of Artificial Intelligence or SOAI, thank you.